in this session of the Victor short course. So we are already in week 8 of our short course. So we have one more month to go. And thanks for those who managed to run the Lahar exercise, the homework. I see on the Padlet that some of you managed to run the exercise that we gave you, so that's great. Keep doing that. Good job. And let us know if you have any questions. We still have the Slack channel open and some office hours, so don't hesitate to ask any questions you want on this on this platform and these options. So today we have the pleasure to have our second guest speaker of this 2026 spring series. It's Matt Gleason, and he's a professor at UC Berkeley. And Matt has been working on some geochemical tools on Victor, and especially MELDS. And so he's going to show us what we can do on Victor if you have some geochemical data and you want to process them using our Victor platform, especially running a Jupyter notebook. So that's pretty cool. Really excited. And so thanks, Matt, for joining us. And yeah, you can start.
Sweet. All right. Yeah, I'm going to start with like 10 to 15 minutes just doing a short presentation about what we've been developing. And then, yeah, my plan is to kind of move over into a notebook and show you some very simple calculations and how they run in Victor and how easy it is to get everything going. So I'm going to share my screen if that's all right. And then just do. Okay, hopefully you guys can see a presentation.
Yep.
All good. Okay, excellent. Yeah, well, thanks a lot for inviting me to do this. One of the things that I've been working on quite a lot in the last couple of years, really since I started at Berkeley, is developing this package, which eventually came to be called PetThermoTools. And really what PetThermoTools is a kind of front end to various different thermodynamic modeling software that allows you to run thermodynamic models, whether this be fractional crystallization, mantle melting, kind of crustal assimilation simulations, anything like this, allows you to run these calculations in Jupyter notebooks with relative ease. So like one of the kind of really nice things we've been doing with this is using it quite a lot for teaching as well. It's very easy to get set up and started, especially with the way it kind of works in Victor. And so we've been using it quite a lot in kind of teaching exercises to get people to think about how does kind of the viscosity of a magma change during fractional crystallization, or what happens to kind of the extent of volatile phase in your system as you decompress towards the surface. How does closed versus open degassing affect these parameters? Things like this. Okay. And so really PetThermoTools is the front end. It's the kind of package I've written to wrap up various different other softwares that allows you to run these models without really having to be really experienced coder in this sense. Okay. And so if you're interested in anything I've talked today, best place to look is our Read the Docs page to have a look. And yeah, I'll kind of get on with it. So the basic idea of thermodynamic modeling, and I say PetThermoTools is kind of just the front end to this, but in the background, what's happening is the idea is if we give some thermodynamic model a composition and we tell it some set of parameters, usually it will be pressure and temperature in most cases. The idea is the thermodynamic models, whether this be the MELT algorithms, being the kind of most well known in kind of igneous petrology, volcanology fields, they'll take that information, search across the different phases that they know about, and find out what is the best way to distribute the kind of chemical composition, the oxide phases. What's the best way to distribute that across different kind of minerals, melt, fluid phases within your system in order to minimize some appropriate thermodynamic potential. Now, I said usually we're dealing with pressure and temperature as our intensive parameters, and so the thermodynamic potential we're minimizing is the Gibbs free energy. And so what these models are doing is basically taking your composition and the parameters you give it and saying, what is the minimum Gibbs free energy state of the system? And that's our equilibrium. It's a way to kind of find the equilibrium of the system. Now that's a very kind of basic approach to it, thinking like almost on a very singular basis. You can take this and like apply it step by step by step to do fractional crystallization or decompression or mantle melting, or any of these different things. You can start building in more complex models, look at how it would look if you assimilate different kind of assimilate wall rocks into your magma chambers. How would that affect not only the composition, but also the energy of the system? Okay. And these thermodynamics aren't necessarily anything new. The MELTS algorithms first came around in 1995, I believe. Excellent work by Mark Grosso. And there are many different ways in which you can run thermodynamic models. And this is a graph I put together when we kind of were submitting an NSF grant to fund some of this work, thinking about all the different ways that you can run MELTS thermodynamic models at present. And in the bottom right corner down here, you have things that are essentially like GUI or spreadsheet-based interfaces. So this is really easy. You kind of type in your composition, you type in a pressure or temperature, you say do crystallization, you hit run, and it prints out this text file with the results. Very easy to run a calculation. Slightly harder to kind of then integrate those results into other code or other kind of bits of software that you might be using, and very tricky in order to do like multiple calculations or to do more kind of intricate style modeling. At the other end of the kind of scale on the top left, we have things like the Enki server, Thermo engine. And Enki is absolutely fantastic. You can basically do any type of thermodynamic modeling that you can envision in Enki. It's incredibly powerful, huge potential for new, exciting science. The kind of problem or challenge, I guess a better way to put this, with Enki is that if you want to do something relatively simple, it actually still requires quite a steep learning curve. You need to know quite a bit about how to kind of set up the code. You need to know some basic Python and stuff. And so for intro users, this isn't necessarily the kind of best starting point. And so what we were trying to do by developing PetThermoTools is we were trying to find something that would fit over there on this kind of top right corner of the diagram, admitting that we were never going to get anything that's as truly flexible and kind of like as truly powerful, can do anything as Enki is, but trying to make something that has a bit more of that flexibility, potentially the option for automation or large numbers of calculations in a single cell, but still making it easy and accessible to use. And I say we've been using this with undergraduate teaching, and it's been working really well. Students have been getting on top of it really nicely. And so that was kind of the aim, to create something. You can see here that this is PetThermoTools, the arrow coming from AlphaMelts from MATLAB/Python. And so this is really a package based off the work of Paula Antashevskina, who developed AlphaMelts for Python. And so everything I'm going to say about PetThermoTools is kind of the key thing to remember is it is a front end for AlphaMelts, essentially. AlphaMelts is this software developed by Paula Antashevskina and Paul Asmo down in Caltech. And around about 6 or 7 years ago, Paula had a major kind of breakthrough in the kind of way that this code is presented. It used to just be a text-based command line interface. Around about 6 or 7 years ago, they started to release MATLAB and Python versions. And it's actually these Python releases that are specific for your operating system that we then use. We then wrap in functions in PetThermoTools, which means if you wanted to run calculations with AlphaMelts, you don't have to understand the command line interface. You don't have to understand a huge amount of Python or MATLAB yourself to write your own codes. The idea is all you might need to do is find what functions we have. So here we have a isobaric crystallization function. We tell it what model we want to use, what thermodynamic model. We give it a starting composition, some pressure values to run the calculations at, the temperature we want to finish at, some information about whether we want fractional crystallization here. And we can run that calculation. That's essentially one line of code. And I have another line of code in here that we have built into PetThermoTools, and we can easily create a plot that looks something like this. And so the idea is that we've taken like AlphaMelts, which is an incredibly powerful package, and made it really simple to use, is the kind of idea. We make it really simple, in this case, to run 4 different thermodynamic models, plot up the results against your real data in essentially 2 lines of code, is the idea here. The other major motivation for developing PetThermoTools was this. When you run the calculations in AlphaMelts or Python, and say a calculation fails, and anyone who's done thermodynamic modeling knows that this happens all the time. Something goes wrong, equilibrium can't be found, and you end up with these kind of minimization failures where essentially the system can't find a suitable solution after X number of iterations and therefore returns an error. In the alpha melt or Python version, what would happen is the code would then print these messages. And essentially what this would mean is if you wanted to run another calculation, say you wanted to change your parameters and try again, you couldn't just run the same set of code in your Jupyter notebook. In order to run that again, you would have to completely restart your entire Python kernel, reload all the packages you'd loaded in, reload all the data that you loaded in, and then rerun your calculation. And so this was kind of becoming quite a tedious process, especially because the work I was doing at the time required me to be running thousands of different thermodynamic simulations. And so this is something we wanted to try and find a way around. And so the way we've done this in PetThermoTools, which had a secondary advantage as well, is by using parallel processing. So many of you may know what parallel processing is. Other times when I've kind of presented this package to people with very little coding experience, so I'll go through it just in case anyone doesn't know what parallel processing is. And in short, the way that most software options for running the MELT thermodynamic models work is something like this. You set up your calculation. This could be in a GUI interface. It could be an Enki. It could be in Alpha Melts itself. And you tell it to run, let's say, 4 crystallization models. And so most software options will do, okay, we'll run number 1. When that finishes, we'll go and run number 2. When that finishes, we'll do number 3, number 4. When every calculation is finished, compile our results into some kind of results output variable that you can then use elsewhere with other parts of your code. The problem is that these calculations are inherently quite unstable and sometimes fail. And if run number 2 failed, well, that would mean run number 3 and run number 4 would never happen, or the way most software options for the MELT thermodynamic models work. And that's part of that kind of like the messages I showed you previously, showing the kind of inability to reload the MELT library. That was one of the kind of like causes of this. And so what we are trying to do is find a way that we could get these models to run without this issue popping up, without one single failure killing every single run in your calculation. And I've spoken to people who have used other MELT software who were trying to run thousands of calculations, and they would set up these calculations to run overnight. They would leave to go home in the evening. They would come back. They would see that 3 calculations ran, the 4th one failed, and then it left 996 calculations unrun. Okay. And so what we try to do to kind of get around this is say, okay, we're not going to run them sequentially like this. We're going to run them in parallel processes. So we set up a calculation on the main process. That information is then sent to a series of sub-processes, and each calculation is run within its own process. This means that, well, it means a couple of things. It means several calculations can be run simultaneously, but it also means that if one of those calculations fails, it terminates that process, but the other calculations can still continue to run. It doesn't care that that single sub-process has failed. The other calculations will still continue. So rather than only getting the calculation results from run 1 and maybe some from run 2 over here, on the right-hand side, we can get the calculation results from all run 1, 3, and 4. And ultimately, we can get the calculation results up to the point of failure for run 2 as well. Now, this has major advantages in terms of the stability of calculations. Once again, we can set up thousands of calculations, let them run, and know that we will get the results for those calculations, even if a whole bunch of them hit calculation failures or error points. We will still get the results from those calculations. The other reason it's quite advantageous is it actually led to a quite significant increase in the speed at which calculations can occur. Just using a typical kind of laptop, Mac, just typical kind of work laptop, we can typically run up to like 8 calculations, 8 thermodynamic models at a time. And depending on your exact system, this will depend slightly on your available memory as well as on the CPU that you have available on your machine. We typically see with 2 to 4 times speed improvement in the calculations that we're able to run. This means that if we were to run, say, 1,000 crystallization models, once again, typically, if everything went perfectly previously, if there were no calculation failures, you could typically get 1,000 crystallization models done in maybe an hour, maybe a couple of hours, something like that. Nowadays, if I do this on my Mac, which once again isn't like a high-powered system at all, I can now get 1,000 crystallization models done in somewhere around 15 to 20 minutes typically. For other laptops, this could be up to like 30 to 40 minutes, depending on the exact specifications. but it means there's a significant reduction in the time it takes to run these calculations. We've not changed anything about the underlying kind of optimization routines in the thermodynamic models. That's still exactly the same. All that's changed is kind of optimizing the CPU of your particular system. And this will happen the same on Victor. So if you were to choose on the Victor server something with a higher number of CPUs, you would be able to get a bit of speed improvement. For the kind of demonstrations we're doing today, that's not going to be necessary. We can do it on the kind of like standard choice on there. But yeah, depending on your system, you can get a relatively significant speed improvement over running these calculations sequentially. And so the idea basically is it should be easy to use, it should be stable so it avoids kind of model failures, and it should be overall, especially when running multiple calculations, faster than doing these things sequentially in other software tools. And so I'm just going to go through one example of how hopefully easy the code can be set up. So here is our kind of, on the right hand side, our graph of the modal proportions of different phases during mantle melting model. All we need to do to create this is to install PetThermoTools. It's going to be done via pip. We then need to make sure in our Jupyter environment we import PetThermoTools into that environment. These next two lines over here I've kept in because this can be necessary if you're running locally. Most of the time, unless these two lines are only necessary if you don't have administrative privileges on your computer. We've found that people that are government employed don't need to use these lines because they don't have administrative privileges on their computers. For most people, you can ignore these. And actually for people working in Victor, you can ignore these two lines as well. This is basically pointing Python towards the alpha melts for Python files. You need to download these onto your computer if you're working locally and tell Python where to find those files in order to run the calculations. The nice thing about Victor is PetThermoTools automatically will search in Victor for where these files are. So you don't need to worry about those two lines at all. It's done automatically if you're working in Victor, which basically means all you need to do is import PetThermoTools as PTT and then run an adiabatic decompression melting model. So here we have pmelts as our thermodynamic model. We're giving it a KLB1 bulk peridotite composition, potential temperature, starting, end, and pressure step. And then we have a phase plot function here where we just give it this results variable and tell it I want to plot against pressure. And that's all the code required in order to produce the graph on the right-hand side. So in reality, in Victor, it would just be importing it, running the calculation, plotting the results. 3 lines of code. That's all you need. And so far, we've developed various different functions to do various different kind of thermodynamic calculations. A brief summary of the majority of those calculations shown in here. Kind of most commonly used we have our kind of crystallization calculations, phase diagram. A lot of people have been using this also to look at like decompression simulations, as well as looking at this to look at like saturation pressures if you have CO2, H2O contents in melt inclusions, for example. And we are continuously developing this resource. It shouldn't be seen as a kind of like static thing. And one of the things I recently added just this last week is this excellent work by Aaron Bell, Laura Waters, and Mark Girosso, where they used melts to look at the chemical potential of magnetite in spinel, phthalate in olivine, and silica in the melt phase. And using those 3 parameters, given a correction to that chemical potential for magnetite and spinel, we're able to use olivine spinel melt equilibria to calculate the oxygen fugacity of a system. This method is now included in PetThermoTools. We have a function to run this calculation. And so if you have that data, olivine spinel data specifically, you can then see or get an estimate of the oxygen fugacity of your system through this tool as well. All right, a couple more things I want to speak about quickly before we go over to the notebook. And the first is, as I said, the main objective of PetThermoTools was to provide a front end for the alpha melts package. And the alpha melts allows you to run the melts thermodynamic models. These have been around, as you can see here, since 1995 or 2002 for pmelts. And actually the melts thermodynamic models were updated in 2012 with the release of rhyolite melts. However, these aren't the only thermodynamic models in the literature. They're just the ones that have traditionally been used for igneous petrology and volcanology. This changed a few years ago with the release of a software option called MageMin, which basically allowed a Julia interface to run other thermodynamic models. So you're running models from Tim Holland, Roger Powell, and others that traditionally were used more in metamorphic petrology, but have since kind of expanded and developed to be used more in igneous systems as well. And what PetThermoTools does, and we're not going to do this in the notebook today, but if anyone's interested, is PetThermoTools can basically switch between these two options. You can either run models in melts through alpha melts, or you can run models through MageMin using alternative thermodynamic model approaches. And this basically means that to get like a comparison, once again, I'm using melting as an example here, to get a comparison between the Green et al. 2025 thermodynamic model and pmelts, all you need to do is change this one model parameter in here. So in this loop, we're just looping from pmelts to green. Everything else is staying the same. All you need to change is the model parameter. PetThermoTools will recognize that and reorganize your inputs. So it will either work with MageMin or it will work with alpha melts for Python. There's nothing else you need to do other than change that model parameter. Okay, final thing I'm going to talk about is integration with other Python toolkits. So here's a kind of simple fractional crystallization example at 4 different pressures. We have some inbuilt plotting tools to visualize the results. We can also integrate these results directly. You don't have to modify the results at all. Integrate the results directly with PySolveSat to calculate sulfur content at sulfide saturation, sorry. And we can also use Thermobar and other packages to look at things such as mineral classification diagrams. Once again, without editing or modifying your outputs, these feed directly into the functions for these other packages and can produce graphs such as those seen here. Now, I've spoken for a little bit longer than I intended to, so I'm going to finish there. I'm just going to quickly remind everyone that if you are interested, either get in touch, check out our Read the Docs page, or alternatively, we do have a YouTube channel for PetThermoTools where we go through many different example notebooks talking about different kind of calculation types. We also have a list on our YouTube page where we have an entire 2-day workshop that we did. All the sessions were recorded, so you can watch through that as well if you're interested. All right. So I'm going to stop there. I guess I let anyone, if anyone has a question, please let me know. Otherwise, I will move over to Victor and start talking through the notebook.
Let me ask you a quick question. How, for those who are not really good in coding, how do we know which line of code do we need to enter in order to get a particular? So I guess the model is just the model name, but then about the results, how is there some documentation about that somewhere where we can know how to plot certain elements or things like that, or
Yes, absolutely. So yeah, to answer that, I'll start sharing again.
Because I guess the line would be different than the line we need to enter if we were using directly melts, right? It's actually
yes. So in our Read the Docs page, there'll be various examples, and so like there'll be kind of examples for how you can run different calculations. This one would be a typical crystallization calculation, and you kind of see the various keyword arguments that you would use in here. And then there'll be like comparable arguments using the MageMin system, which once again, ignore some of the input print messages, but you can kind of then see the kind of changes in what you would use in this sense. One thing that I did add quite recently is this how to effectively use PetThermoTools page. And one of the nice things about this is, once again, just goes through, in this case, a simple decompression calculation, is this kind of talks through the different like output structures. And so in here, this example talks through like what the output looks like at different steps. So what kind of different parameters are within the outputs, and how you might go about calling different outputs to look, in this case, at like the composition of your fluids phase, for example, during a decompression calculation, and how you could then take these results, and when you have multiple thermodynamic models, how you might go and create a simple for loop to go and loop through your calculations to create a simple plot like we were showing here. So we do have some documentation that goes specifically through like the input parameters and also in this case, the output parameters. The other thing that you can also do is all of these functions have documentation. So if I go into our notebook for today, which hopefully I've got the right place here. Yeah, so for anyone following along, the first thing in this notebook that you need to do is actually just run this pip install PetThermoTools line. So the alpha melts files are by default included in Victor. PetThermoTools at the moment isn't, so you just need to install it via pip. It should take 5 seconds, and that's done. And then that's all the installation you'll need to do in Victor for PetThermoTools. But the reason why I did that, I'm just going to comment out quickly, is what you can also do if you kind of are looking at like, oh, I've got this function, what parameters do I need to use for it, is once you have imported, I'm going to add this in here. Once you've imported PetThermoTools into your Jupyter environment, sorry, I got there eventually. What you can always do is use the Python help function. And once you know the name of if I can spell correctly, once you know the name of a function, which you can typically find through read the docs, if you use the help function here, it will then print out this documentation and it will say things like, okay, here are the different thermodynamic models that you can use as an option in the model parameter. The bulk composition needs to be either a dictionary or pandas data frame. And we'll go through typically what the default parameters are for some of these input parameters, how they are used, and yeah, what options you have, essentially. Does that kind of answer your question?
Yeah, definitely. Yeah, thanks. Great.
Awesome. Yeah, so one thing that can be quite useful is having the reader docs, and then if you don't understand anything, I actually do this in a separate notebook, so I'll explain why in a second. But having a separate notebook open and you can just run these 2 lines with whatever function you're using at that time, and it should print out some example documentation or some documentation giving you kind of idea of what different options you have available to you at that step, essentially.
Yeah, that's great to have them integrated into the notebooks. That's really good.
Yeah, so yeah, as I said, I would usually do that in a separate notebook. I'll explain why in a second. But I guess, yeah, we've got half an hour down, half an hour left. If there are any other questions, or should I move on to working through the notebook and giving people a chance to follow along? All right. Good. If anyone has a question or is falling behind or something that doesn't make sense, please stop me. I love doing online workshop stuff because I can reach so many more people like this. But I also appreciate that it's very easy to kind of like disengage when if you fall behind or don't get something, and it's sometimes really hard online to speak out. So do not worry about interrupting me. Please do. Essentially. Okay. Cool. Okay, so yeah, hopefully everyone's got this notebook, which is in the week 8 shared folder. And as I said, the first thing you need to do is pip install PetThermoTools. So just run that one line once. After that, you can comment it out if you want to. And that is all the installation you need on Victor for PetThermoTools. Usually, and if I kind of go to read docs here, there's actually a for locally installing things, there's this relatively long installation process. So installing Python, once again, pip installing PetThermoTools, and then especially if you're on Mac, there's this like secondary step where you have to use Homebrew to install GSL before you can then run my install command down here. Okay, so this is how you would do it locally. Everything in that process, you don't have to worry about doing it on Victor. It's not that tricky. If you want to do it locally, it takes around 2 to 5 minutes, depending on your computer. It's relatively straightforward. On Victor, you don't need to worry about it. So the first thing to run is like just importing our different packages we'll use. We're also going to use Thermobar, which was developed by Penny Weezer at the end of this notebook if we get there, so we'll import that as well. And so if you run this cell, it should, one sec, I'm going to restart my kernel, so it's importing it for the first time. So I'm going to run this cell, and if this is the first time you've imported PetThermoTools since restarting the kernel, it should hopefully print this line. Okay. This line here is telling you that it knows where to look to find the alpha melts file. So it knows where to look to run those calculations. We're not going to run the green or weather MageMin models in this notebook. If you're doing so, there are a few other installation steps that you need to kind of go through. It's a bit harder because we're trying to link Python to Julia to do these calculations. So it's a little bit more involved. I'm not going to go through them today, but if you're interested, look at our documentation, contact me, let me know. Now, the one thing that we can do, so I'm going to skip over this cell initially. I'll come back to it in a second. What we're actually going to do here is we're going to load in some glass data from the islands of Fernandina in the Galapagos archipelago. This is one of the most active volcanic systems in the Galapagos, and these are actually all submarine glasses and melt inclusions from a submarine eruption as well. And all I'm going to do is sort them by their magnesium contents and take the first composition. So this is just choosing a starting composition for a fractional crystallization model, essentially. So I'm just loading in glass data, sorting by magnesium, and then taking the first value to get the most magnesium-rich basalt for our starting composition. Okay. Now, in this next cell, this is actually going to run some models. And what I'm going to do when I run this is you're going to see it's going to print out. It should print out. Why is that not working? Okay, bear with me 1 second.
Is it because you're in like a read-only folder? Is it supposed to output any files?
Oh, possibly. Yes.
Yeah, then you might need to copy it over to
Okay.
your home directory. Yeah, because right now it's in the shared area, which we try to keep as a
that makes sense. Okay, so in that case, yeah, if you copy these, so both the notebook and the spreadsheet over into some home directory. So for me, I'm going to terminate that so it's not just continuously running. I have this one I set up the other day. Which one of these is this one? Okay, sorry about that, everyone. So I'll just quickly run through to where I was. There we go. So yeah, once yes, you're correct. It's writing this liquid model batch file as it runs. So when you run the thermodynamic models, it prints out every single step of the iteration, every single step of the minimization. This can be quite useful for debugging, but you can kind of see that if you're just trying to go through a notebook and you've got to scroll through all of this, it can get quite frustrating. Okay. So this is where these lines that I had above, this line of cell here, this is where this comes in. These basically suppress the outputs in terms of the outputs that are printed within the notebook. I don't understand why, but in order to suppress them fully, you have to run this cell twice. Okay, this is one of the things that I'm actively working on finding a better solution for. If you're on Windows and you're working locally, this isn't an issue. If you're on Linux or Mac, and Victor works on Linux, this is an issue. So just run that cell twice, it will suppress the outputs. This is why I suggest when you're doing the help command, doing it in a different notebook, because otherwise the help command won't give you anything after you've run this cell. So it's a little oddity of PetThermoTools, and specifically it's the alpha melt C code that's actually printing these messages. And just to kind of keep the notebooks clean, I suggest running that cell twice. So if you run that cell twice, import our starting composition. So here, once again, just isolating most magnesium-rich basalt. We can then run this model. And so if we run this cell, I'll quickly talk through what's actually happening. So it should take around 5 seconds to run. I believe in this case, there we go. So it's finished. And so we're saying, okay, we're going to call a variable crystal single, and we're going to run isobaric crystallization. Melt v 1.2.0 refers to the rhyolite melts version 1.2.0, which is the version which includes the most recent up-to-date mixed fluid solubility model. So the H2O CO2 solubility model that was released in 2015, I believe. We need to give it a bulk composition. This is the comp variable that we defined above. So this has to make sure you should have a column for silica, for titanium, for aluminum. And it needs to be in this format, either like this or SiO2 underscore LIQ. If it has like SiO2 weight percent or something, it's not going to recognize it. So just in terms of your column formats when you're kind of loading in your data, just keeping it clean to the oxide like this is the best way to do it. In this case, there are various other kind of arguments we can use. This is a true-false argument. If we set true, we are going to start at the liquidus. We're initially going to search for that liquidus point and then start our calculation from there. If we had said false, the code would actually have thrown up an error because it was said, I don't know where you want me to start. We haven't given it a starting temperature. We've just given it find the liquidus, end temperature, and a temperature step. And if we don't say find liquidus, we need to tell it where to start the temperatures, what temperature to start essentially. So it's going to ask you to either give it find liquidus equals true or tell it a starting temperature. We're going to run at a single pressure in bars here, and we are going to specify an initial ion redox state to the system. The final thing we're going to do is we're going to tell it to do fractional crystallization by telling it to fractionate solids. There is actually a separate argument for frac fluids as well, if you wanted to fractionate fluids from your system as well. So we're going to treat those slightly separately in this case. Okay, so hopefully people have managed to run this and this is run successfully. Now, if you have things in a local or personal folder, I'm going to quickly talk through the kind of output structure, and hopefully this gives everyone a chance to copy those into a local folder, or sorry, a personal non-shared folder, and run those calculations. If you're having issues, please stop me, let me know, and we can kind of sort out what's going on. Okay, so this output here is actually what we term a dictionary in Python. So this is something that has a key and a value pair. So there'll be some kind of string or value that's like identified a certain parameter, and then that parameter will be kind of identified with that key, essentially. And so we can look at the different keys in this dictionary to understand what do we have in our outputs. Okay. And what we have in our outputs are various different data frames. For every phase that's saturated, we'll get the composition of that phase, and we'll get the properties of that phase at every step that it's saturated. In addition to this, we'll get the overall conditions of the system. This will include the pressure and temperature, but also thermodynamic parameters like the entropy, enthalpy, the volume, the mass of the system at different steps. Obviously, the mass will be decreasing as we're undergoing fractionation. We'll also have these other data frames at the bottom. So the mass G would be the mass of each phase at every step of the calculation. This can be quite a nice one to look at. So if we do that quickly here, all we need to do is get the name of our overall variable. And then in square brackets, type that string for that data frame. And here you can see that we have two different chlorpyroxene saturating. We'll obviously start with 100 liquid. This is technically in grams, just so you know. So 100 grams of liquid. And as we cool down, as we go to lower temperature, which is going down this diagram, we start to crystallize olivine. And by the end of this here, we're crystallizing two types of pyroxene, plagioclase, some kind of hematite-like hematite phase, and some magnetite type phase as well. Okay. We also calculate here, because we're doing fractional crystallization, is the cumulative sum of each of these phases. Okay, so by the end of this crystallization sequence, we've got around 21 grams of pyroxene, around 10.5 grams of olivine, and around 31.5 grams of plagioclase. Okay, so these extra kind of data frames here for the mass, the volume, and the density are these kind of summary of those parameters across all phases that saturate in the model. We also have a data frame all, which literally combines all the information outputted into one data frame. So this will be our kind of system conditions. It'll be the parameters of each individual phase, the thermodynamic properties of each individual phase, all combined in one data frame. I don't typically use this, but other people have requested it because they want to then export that into a single Excel notebook, into a single Excel sheet, and have like the results of one calculation all in one place. And that's why we have this. If you want to export this into Excel, you can do so relatively easily. Okay. So a nice way to kind of examine this, if we wanted to look at a single parameter, is maybe to look at the liquid parameter. And so if we just type .head here, it just shows us the first 5 lines. And so the outputs here are always shown in weight % for the composition of the different phases. And so here you can see we've got the silica, and we always kind of have these underscore phase name to identify what phase we're looking at. So here we have our liquid composition at each step. If I were to type in olivine 1, you'd see the same. We go olivine phase, and rows where there's nans, that phase was not saturated. Okay. So we'll also get the iron 2 plus and iron 3 plus, and a total iron number, and a iron 3 iron total ratio calculated for each phase. Obviously for olivine, this should be 0 over here because Melts doesn't know about any ferric iron in olivine. Okay. So all of these outputs here, and there's a few others that might be interested in, so like phase list, for example. I'll get rid of the head here. We'll just print what phases are saturated at each step in the model, so you can look at what phases your model is crystallizing at every step. All of these outputs, hopefully, once you kind of get used to the output structure, are relatively easy to access and use in more detail. And all of the parameters we have should have the units associated with them in the headers, with the exception of the compositional data frames, which are always in weight %. Okay. Hopefully I've waffled on for long enough that everyone's been able to run this calculation. If there's anyone that hasn't been able to run this calculation, please let me know. I'll try and sort it out. The other thing we can do with this calculation, so we now have our output variable crystal single, is we can just use this inbuilt Harker function here to just create a nice plot. And so we can now see that by default, it will plot the liquid composition. You can actually specify a phase here. By default, it will be liquid. We can specify olivine, we can specify chylopyroxene. And you can also see in here that we can specify what we want to plot on the y-axis. By default, it's basically every oxide with the x-axis being magnesium. If you wanted to change this to silicon on the x-axis and change your y-axis values, you can as well. You want to see we can change the color of the line, and I'll talk a little bit about this data parameter in a little bit. Okay. But yeah, there's some flexibility in this plotting function as well, but just as a very basic example here, it will show you what's happening to your melt composition during crystallization. Okay. This may look almost identical, and that's because it is almost identical. Okay. So this function here, we're going to create a new variable, crystal multi. We're going to use the same function. We're going to use the same model. We're going to use the same initial composition. We're going to tell it to start the liquidus, go to the same final temperature, the same pressure step, the same initial ion redox state, and we're going to fractional crystallization once again. The difference is that we're going to provide it with 4 different pressures rather than just 1. And all this means is that when we run this calculation here, it's going to run the calculation 4 times. Okay. It's going to run it once at 500 bars, once at 1,000, once at 2,000, and once at 4,000. It's going to run those 4 calculations, and it's going to store them within this single results dictionary. Okay. So you can see this crystal multi. If I look at the keys of this output, it now has run 0, run 1, run 2, run 3. Python counts from 0, so we start at 0. This looks quite different to the output parameters up here. Okay. But if I were to add another cell in, and I was to look at multi run 0 dot keys, this now is identical to what we had above. Okay, so each of these different values in this output dictionary here, each different key identifies the output for a single thermodynamic model. Okay, Now, I'm going to show you a couple of things. Firstly, I'm going to break the code, and then I'm going to add something in to make it a little bit more useful. Okay. So the first thing I'm going to do is I'm going to get rid of this line where we specify the iron redox states. I'm going to try and run the cell, and it's going to print an error. And it's one of these kind of fail safes we've built into PetThermoTools, where melts actually is really unstable when no ferric iron is present in the system. And so what you need to do is you need to make sure you're either providing that Fe3 FET init value, or you're providing an FO2 buffer. Okay. So in here, we could have, instead of the Fe3 FET init, you could specify a buffer of FMQ. You could also specify an offset in log units from that buffer, and that's, and now the calculation should run. So we either need to tell it something about how much ferric iron is initially present in the system, or we need to tell it a buffer along which to run those calculations. Okay. And that calculation will run, and it will print out the same apparent outputs, but they will be slightly different in terms of the overall numbers in these values because we're actually buffering our system along that FMQ -1 buffer position. The final thing I'm going to change here is I'm going to add a new keyword argument. I'm going to add a keyword argument called label. Okay. And this keyword argument here, label, actually allows us to label these outputs when we're doing multiple runs. Okay. So run 0, run 1, run 2, run 3 doesn't really mean much, right? What we've actually done in this calculation is we've varied the pressure of the system. And so what you can do with the label keyword argument is you can basically choose any of these input arguments and choose which one you want to label the outputs by. So if I put label equals P bar and rerun this calculation, and once again, it'll take around 10 seconds to run, but these output keys in Crystal Multi will now hopefully mean something a bit more meaningful. Okay, so the output keys, rather than being run 0, run 1, run 2, run 3, once it finishes in a second or two, will now be respective to the pressure of each calculation. Okay. So now if I wanted to access the pressure of the first calculation, I'd have to type that. And so what we can do here is, once again, it's emphasizing once we run multiple calculations, you just need to add in this little bit in here within the square brackets to tell it which calculation you want to look at. And then this output is identical to the output for the single calculation up here. It's basically this hierarchy of dictionaries. We're now gone one step up. And so we need to kind of access that second step in order to access the individual thermodynamic models. The Harker function here, once again, we can just provide the output dictionary. We don't have to specify which model we want it to plot. We don't have to specify anything else. If we just provide the output dictionary, it will now plot up those results, and it will plot all the different thermodynamic models, provide you a label for them. We can, once again, we can start to change this. We can specify a y-axis value. If I type that correctly. And let's say we just want SiO2, TiO2, FeOT, and well, calcium, say. And we run that. By default, PetThermoTools is going to recognize if I provide 4 things in the y-axis column, it's going to default to a 2x2 grid. If I were to provide more than that, it will basically try and choose what kind of shape is best for your graph. And so if I provide 5, it will do a 3x3, and the final empty spot it will use for the legend in here. Okay. So you have quite a bit of flexibility in these plots that you're creating as to how you're actually kind of designing them. It will do it in the order that you specify here. And let's say you can also change the x-axis value. We just do that quickly. And make this something stupid. Let's make it potassium, because why not? It will work. It will look stupid. It's not a great way of showing your data, but you can kind of do that if you want to. All right. Does anyone have any questions, or has anyone had any issues with any of this so far? I realize I'm going through things quite quickly. hopefully with the recording and everything else, people will have a chance to go through these calculations themselves. But yeah, if there's any issues, please do let me know.
Roberto, you have a question?
Yes. I just changed some of the lines that in the where you change the FO2 buffer and FO2 offset. I literally just copied just as you have it on screen, but I get an error back. So I don't know. It says that it's gonna recognize the label chosen.
Sorry, I can't quite hear you. I think you're saying you're getting an error here.
Yep. Yep.
Okay. There's a couple of things that may be the case. Like FO2 buffer has to be FMQ or NNO. If you put QFM, it won't work. And then other things like that. The FO2 offset, it can be any value. It doesn't have to be an integer or anything. The other things to just check for is like make sure you're not missing a comma or something. If you are deleting and adding lines, it might be that you've accidentally deleted the comma there and then it's giving an error, things like this. The code should run with how it is exactly here. So I'll leave this up for a second and give you a chance to just double check that everything matches exactly as it is. You're not missing a comma or anything like that, or FMQ spelled wrong or something. Or those are probably the most common things that may have happened in this case.
Thank you. I'll check.
All right. Has everyone else had has I don't know if you guys can do like thumbs up or something through there, people being able to run these calculations effectively?
Question. Yeah, it worked well for me as well. So that timestamp that you have here, the DTC,
Yes.
is that the default one? And you would recommend not changing that? I mean, how much that's going to impact the
yeah. So this, I admit I should have made this a capital T because this is the temperature step. That is on me being lazy. I recognize that DTC does look like change in time, not change in temperature. But by the time I realized that I had done that, too many people were using the code and it was too late to change it.
Okay, so it's a change of temperature, right?
Change of temperature every step. And by default, I think we set it to 2. So actually, there's a good point that actually, if I didn't include this line, the code would still run. There is a default parameter set in here. 2 is usually a good number. There is a trade-off between how big you set this number and how quickly your models run. The larger you set the number, the faster the models will run. However, if you're doing fractional crystallization, you're dropping 10, 20 degrees on each step. You're not truly doing fractional crystallization at that point. You're kind of doing periodic batch crystallization. And so if you want to do like a fractional crystallization or fractional melting or fractional decompression scenario, you want to make sure that DT, and there is like a DP bar parameter as well for decompression calculations. You want to make sure that number is relatively small. I don't think it's usually the slow point of the code is how many calculations it does in a single model. So I would usually keep this around 2. I would only change it if you're really interested in what happens over a very narrow temperature interval in your system, then I would make it smaller. Otherwise, I don't see a great reason for making this significantly bigger in this case. Okay. All right. So a couple extra things I did just want to show. So I'm going to go through them just quickly. And so they're on the recording so everyone can see them as well. And so we have our nice plot here of 4 different thermodynamic models. We run this again. It should put magnesium back on the x-axis to make this nicer. What we can do, and I haven't done so far, is add this parameter data. Now to explain this a little bit, let's actually look at the data frame of glass compositions we loaded in earlier. And you can see that there's this parameter group in here. We have either mg, standing for matrix glass, or mi, standing for melt inclusion. And so what I'm doing here, so I'm going to make this line up a bit nicer, is I'm actually just going to, for my data parameter, I'm just going to make it a dictionary. That's what the curly brackets mean. And I'm going to call one value in the dictionary mg. And for this, just locate all the values in that data frame up here, where the group is equal to mg. The second parameter I'm going to call mi. And this is where all the group is equal to mi, essentially. So this data parameter, let's put this on one line to make it a bit nicer to look at. It's just splitting this data frame into two variables, one with mg, one with mi as the group. And then just by setting that as our data in this Harker plot, when we run it, not only do we get the plots of the thermodynamic model predictions, we also get plots of the actual geochemical data from this island of Fernandina in the Galapagos archipelago. So if you wanted to compare your fractional crystallization models against real data, it's relatively easy to do that in this plot up here. And if you just had a data set and you didn't want to split it into two separate things, well, that's also easy as well. If I copy this code into here, if I didn't care about showing melt inclusions and matrix glass separately, I could just provide a data frame there and it would plot everything as a single color, essentially. And I would just call it data. Whereas in this one down here, where I've separated them into the two groups, it would separate them into the matrix glass and the melt inclusions, essentially. Okay, I have 1 more minute, and I want to show you one more thing in this. So one of the nice things that we have in PetThermoTools is the outputs. The reason why we use this underscore CPX or underscore liquid, or underscore lick, sorry, for all the outputs, is this means that PetThermoTools works really nicely with some other Python packages developed primarily by Penny Weezer. This is a kind of clinopyroxene composition from the P equals 500 bars. Okay? And basically what this means is that these compositions fit into and interact directly with functions from other Python packages. Specifically, the one we're going to look at here is thermobar. And so in this plot down here, we're going to use PT is thermobar. We're going to use this plot classification, pyroxene classification here. And if I were just to comment out these lines, basically this is creating this pyroxene quadrilateral plot. What we can do in this for loop is saying for model in crystal multi.keys is if we take crystal multi model, that will give us each, and every loop this will access a different thermodynamic model. And we look at the clinopyroxene composition here. Suddenly now our thermodynamic models, which will run in melts, we have our outputs. I had to change absolutely nothing about the outputs, load them directly into this thermobar ternary point pyroxene function, and then we can plot up our pyroxene data in pyroxene quadrilateral. And you see that actually at high pressure, we start to stabilize this kind of dual CPX. We have this typical kind of augite and a low calcium pigeonite stabilizing at the high pressure simulations as well. Okay. So it's a kind of nice demonstration here, just like the reason why we choose these kind of output suffixes on the output variables is because it allows it to integrate really nicely with other Python packages, thermobar being the example here. Okay. I'll leave that up in case anyone wants to have a go copying it, but if anyone has any questions or anything else you want to ask, feel free to let me know. And I'll say I am always happy to chat to people via email. We also have a separate Discord for Alpha Melts and PetThermoTools. So if you're interested, contact me. I'll get you the Discord link. Check out our YouTube page if you want more examples, and I'll read the docs page for more documentation on how to run these kind of calculations. We also, if anyone is in a kind of teaching role at any point, we have a page on Read the Docs for PetThermoTools in the classroom, where we have all the notebooks we have used in various classes here at UC Berkeley. We have those notebooks available so you can download them, and along with the kind of like student exercises that we do using PetThermoTools as a teaching tool as well as a research tool.
That was actually my question. I wanted to ask you if there was some teaching modules or notebooks that you guys already put together. So
Yeah, so
great.
I might as well show this. So I would say like anything on the reader docs could be turned into a teaching thing. So we kind of have our like a simple decompression calculation for Mount St. Helens, and you can look at like changing fluid composition, melt water content, how this actually affects like silica content. And also in this, we kind of then do more things to kind of show how you can calculate mass proportions. And well, I'm looking for something specific here. Here we go. The viscosity of the magma during decompression as well. So like all of these notebooks in some way could be turned into teaching tools quite easily. We specifically have in this structure, if I go back to the homepage, one of the things we do have is our YouTube. And then the second thing we have is PetThermoTools in the classroom. And so this page here will have our different practicals that have been used in classes here at UC Berkeley. And we'll talk a little bit about what they've been doing. You can see a nice advert here for Victor. We say that if students don't have any Python experience, we encourage them to sign up for Victor because the installation and setup is so easy in this case. And then we have the kind of notebooks that we use. So these are all hosted on GitHub, as well as the answer keys for this. And yeah, so a notebook, the kind of doc file with their the questions they need to answer, and the answer key in here. And so in this case, this notebook here, if I move over to it, this actually talks or gets people to talk through crystallization, and what initially looks at like the parameters for basalt rhyolites, looks at the liquidus phase for the different systems. And then the key thing this notebook does is actually looks through, if I can find it, crystallization under different conditions and how that may be related to foliatic and calc-alkaline differentiation series. Another nice example here, we have this kind of phase plot, which I showed briefly for the melting. You can also do it for crystallization, and it will show your kind of cumulative sum of crystal proportions across that crystallization model in here. And eventually, I believe in here, yeah, nice TAS diagram as well. So a lot of these things, and here, this was like the final plot of their notebook there to do. It's kind of foliatic versus calc-alkaline differentiation series. But yeah, things like that we have. So it's like there we have one volatile solubility as well. And we will be adding to this as we go. We've only really started using it for teaching this year, but this PetThermoTools in the classroom page on Read the Docs will continue to grow. And if anyone uses it for this purpose, we very much encourage people to send us what they're doing, especially if it works well. Work with us if you're kind of developing something and you can't get something to work correctly. Let us know, see if we can fix it. And then if you guys give us permission to, we will then host it on the Reader Docs page so other people can use that teaching material as well.
Very cool. That's really nice. Yeah. Cool.
Right.
Are there any other questions for Matt? I'm good. Okay. All right. Well, thank you, Matt. Thank you very much. Yeah, so you can use all the links and that Matt was showing. And if you have any questions, don't hesitate to either reach to us on the Slack channel or directly on the with Matt on his email address. Thank you very much, and see you all next week then for the next session.
Thanks a lot for having me. That was good fun.
Thanks
Thank you. That was a great one.
Bye, all.